My goals this summer are to vary the parameters of a ring resonator and to find which parameters cause the most variations. So far this summer, I've built a model for a ring resonator on numerical software, and I have analyzed a few parameters on how their variations might affect the performance of the device. I've had some interesting results so far, looking at how only really two parameters stuck out and caused large changes, which is not a good thing, but it's something that we are looking for. I've learned a lot since I've got here. I've learned how to use all the software. This is a ring resonator, and the parameters that I've found that vary the performance the most so far has been the width and the thickness of the whole waveguide and resonators.
Variations in silicon photonics are very important because the eventual goal would be to implement these structures in the same sort of process that we have CMOS, for example, transistors and electronics done. The idea would be to have both silicon photonic structures and CMOS structures on the same chip at the same time working together. So CMOS tends to have metal connectors connecting the different transistors together. Those metal interconnects take up a lot of power. They heat up, especially when you're running at gigahertz frequencies. One application of silicon photonics would be to replace some of these metal connectors with silicon waveguide, for example. And the benefit of that would be that you don't dissipate nearly as much heat because you're not heating up metal anymore. You're using light, which doesn't heat up.
For a system on a chip with theoretically a lot of different cores, that would be perfect for routing these cores together.
But what is different about the ring is that it will only pick up light at certain wavelengths.
Ring resonators directly apply to this data application that Jermaine was talking about. They can sort through the wavelengths and essentially modulate the data, and that's like what radios do. They modulate a signal. With a heater or with other ways to actively tune these resonators, you can change what wavelengths they let through. I currently am working at implementing a heater in the device and in my models so as I can heat the device and mitigate these variations, and hopefully that will solve these problems in manufacturing.
If we had a way to generate these things more quickly and with less variations, we could make an entire fiber optic chip that could handle an entire network and put out a bunch of these at once and save internet companies a lot more money and a lot more infrastructure.
And then lastly, if I can make a mathematical model to describe the variations of these devices, then that would be very useful in the design of these devices.